Hi, this is Revathi from the CSE IoT branch. Today, I'll be presenting on the topic cybersecurity in smart grid systems. Smart grids are the future of electricity distribution, making our power systems more efficient and intelligent with the help of IoT devices, sensors, and real-time data. But with this innovation comes new risks, and that's why cybersecurity plays such a critical role. In this video, I'll explain the basics of smart grids, the major cybersecurity threats they face, recent advances in protecting them, real-world examples, and finally, what the future looks like for secure energy networks. A smart grid is an upgraded version of the traditional electricity grid. In a traditional grid, electricity flows only one way, from power plants to homes. But in a smart grid, electricity and data flow in both directions. This means homes, businesses, and even electric vehicles can both consume and supply energy back to the network. Smart grids rely on IoT devices, advanced sensors, and real-time monitoring, making the system more efficient, reliable, and sustainable. Installed in homes and businesses to track energy usage in real time. Second, SCADA systems, supervisory control and data acquisition, which monitor and control power distribution across the grid. Third, IoT sensors, placed along transmission lines and substations, which measure voltage, load, and faults. Finally, communication networks like fiber optics and 5G, which connect all devices and enable secure, real-time data exchange. Together, these components make the smart grid more intelligent, responsive, and resilient. Smart grids bring intelligence and efficiency, but they also expand the attack surface for hackers. One major threat is malware and ransomware, where attackers disable control systems or demand payment. Another is man-in-the-middle attacks, where communication between devices is intercepted and altered. We also see denial-of-service attacks, which overwhelm the grid with fake traffic, disrupting operations. And finally, false data injection, where hackers manipulate meter readings or sensor data to destabilize the system. Each of these threats highlights why cybersecurity is critical for smart grids. Cybersecurity in smart grids isn't just a technical issue, it affects our daily lives. A single attack can cause blackouts, financial losses, and even risks to public safety in hospitals, transportation, and communication. That's why securing smart grids is a matter of national security as well as personal convenience. Smart grids are becoming more secure thanks to several innovations. Artificial intelligence and machine learning detect anomalies in grid data. Blockchain ensures secure energy transactions. Quantum cryptography offers next-gen encryption. Zero trust requires continuous verification of devices, and edge computing speeds up local responses. We're already seeing these advances in action. In the US, utilities adopted AI-based predictive security in 2023. India's smart grid mission now mandates cybersecurity audits. And the 2015 Ukraine attack still reminds us of what can happen if defenses are weak. In the future, smart grids will connect renewable energy, electric vehicles, and smart homes, increasing both efficiency and vulnerability. That's why cybersecurity is not optional, it is the backbone of modern energy resilience. With advanced defenses, secure smart grids can power societies reliably and safely. In the future, smart grids will become even more connected and complex. We will see renewable energy sources like solar panels and wind turbines feeding directly into the grid, while electric vehicles not only consume power but also supply it back when needed. Smart homes and IoT devices will play a larger role in balancing demand and supply. But with this growth comes more vulnerability. The attack surface will expand, making cybersecurity more critical than ever. Emerging technologies like artificial intelligence, blockchain, and quantum cryptography will be essential to ensure that future grids remain resilient, reliable, and safe. In conclusion, smart grids are the backbone of our future energy systems. They bring efficiency, sustainability, and intelligence to electricity distribution. But without strong cybersecurity, they remain vulnerable to devastating attacks. By combining innovations like AI, blockchain, and quantum cryptography with careful monitoring and zero-trust security, we can ensure that smart grids remain safe and reliable. Cybersecurity isn't just about protecting data, it's about keeping the lights on for millions of people, and ensuring the stability of our society. Let's look at some real-world cases of smart grid cybersecurity. In 2015, Ukraine's power grid was attacked with malware called Black Energy. Hackers gained control of substations, leaving more than 200,000 people without electricity. This was one of the first known cyber attacks on a nation's power grid. In the United States, utilities began deploying AI-driven cybersecurity systems by 2023. These systems monitor network traffic and flag suspicious behavior before it becomes a full-scale attack. And in India, the Smart Grid mission now requires regular cybersecurity audits to safeguard its rapidly growing energy network. These measures highlight the urgent need for strong defenses as countries modernize their power systems. Let's quickly recap what we've covered. We began by understanding what a smart grid is: a modern, two-way electricity network that integrates IoT devices, smart meters, and real-time communication. We then looked at the components that make up a smart grid, including meters, sensors, SCADA systems, and communication networks. Next, we explored the cybersecurity threats these grids face, such as malware, denial-of-service attacks, man-in-the-middle interception, and false data injection. We also saw how recent advances like AI, blockchain, quantum cryptography, zero-trust models, and edge computing are making grids more secure. Through real-world examples in Ukraine, the US, and India, we saw how cybersecurity challenges are not just theoretical.